So we are in the what you call this is engineering statistics and linear algebra 18 EC 44. We are in the module 2, lecture 5. In the lecture 1, we did the bivariate PDF and CDF, and then the bivariate expectation in lecture 2, and then in lecture 3 we saw the bivariate transformation, right? So then we considered the Gaussian independent random variables in the lecture 4. Now we are in the lecture 5, which corresponds to sum of two independent random variables. Okay, the sum of two independent random variables will involve, might be, random variables x and y, where if you say sum, then to the w is equal to x plus y. So a general class of problems in engineering occurs when we have two independent random variables which are added together. So w is equal to x plus y. Now this might be the case when we say that x is the signal and y is a noise component, a random, noise. So x is a what you call signal and y corresponds to noise. Also there might be, so that is what is the example given over here. Might be s, we write here, they have used a symbol, the book has used a symbol v, but we can as well use say n here for noise. Okay, capital N also can be used for noise. Further to that, x and y can also be two different observations of the same what you call type of event, but the what you call the observations themselves might be independent. For example, it might be tossing of two dices, might be tossing of what you call two coins. Okay, throwing of two dices or tossing of two coins, or might be using two different set of pack of cards for playing a game. Okay, so then at that time we might try to write w is equal to x1 plus x2. Okay, w is equal to x1 plus x2. So sum of two independent, remember that only this x and y, sv, x1, x2 are independent. Okay, independent random variables. Okay, they are independent random variables. So when they are independent, then we can take the expectation on both the sides. And if you take expectation on both the sides, then it just gives us the mean of the what you call w is equal to mean of x plus mean of y. Similarly, if we what you call want to write the variance of the w signal, okay, sigma w squared is the variance, then that will just correspond to the expectation of w minus mu w whole squared. And for this w we can substitute from the equation 3.78, which is written 3.78, which is written over here, that is x plus y. W is equal to x plus y, and for mu w you can substitute from 3.79, that is minus mu x minus mu y whole square. So we are trying to keep the x minus mu x together and y minus mu y together, and that will make us x minus mu x plus y minus mu y whole squared. So x minus mu y, mu x can be considered as a, and y minus mu y can be considered as b. So a plus b whole squared will give you a squared plus 2ab plus b squared, and that will give us x minus mu x whole squared into 2 into plus 2 into x minus mu x, y minus mu y plus y minus mu y whole squared. So this is like a plus b whole squared. So this again, if you take the expectation of this quantity, that is x minus mu x whole squared, that is nothing but the variance of x value. Variance of x value, which is sigma x squared, and 2 into the expectation of this quantity. Expectation of this quantity is nothing but covariance. Okay, 2 into the covariance, because expectation of x minus mu x, y minus mu y is the covariance. Similarly, expectation of y minus mu y whole squared is the variance of the y variable, that is sigma y squared. Okay, y independent random variable. So now we have already said that the x and y are two independent random variables in our definition itself. We have considered sum of two independent random variables. So once we say independent, naturally covariance will be equal to 0. When covariance is equal to 0, then this quantity is 0 and we are left with sigma x squared plus sigma y squared. So sigma w squared is equal to sigma x squared plus sigma y squared because covariance is equal to 0, because x and y are independent variables. Okay, so independent variables, therefore uncorrelated, and hence the covariance is equal to 0, and therefore variance of the what you call variable w, which is will be equal to the variance of the x plus the variance of y. Okay, variance of x plus variance of y. Okay, the squared term is variance. If you just take sigma x, that will be standard deviation. So we want to find the PDF of the random variable w, assuming that PDFs for x and y are known. Okay, so the what you call, starting from the CDF. Okay, we are now, before finding the PDF, we will try to start from the CDF, that is the cumulative distribution function for the random variable w. Okay, so FWW is the cumulative distribution function for the random variable w, and that is written as Px plus y. That is because this can be written as capital W P, capital W less than or equal to W, and capital W is itself nothing but x plus y, which we have considered over here, right? So in place of W, we have written here capital W, we have written here the x plus y. Now taking that, P of x plus y less than W, and that is nothing but P of, both the, what you call, the region we need to consider, that is x plus y less than W. Okay, the region R over which x plus y less than W is considered, okay, in the figure which is written over here. Okay, so if you see this, we can try to write W is equal to x plus y. W is equal to x plus y is the line which is here. X plus y is equal to W is the line which is written over here. Okay, so that just gives us that if x is equal to 0, W is equal to y, right? If x is equal to 0, W is equal to y, and if y is equal to 0, W is equal to x, right? So this point and this point, if you just join and extend it, you'll get this. Whatever is below this line is x plus y less than W. Whatever is above this line is x plus y, greater than W. Okay, whatever is above this line is x plus y greater than W. Whatever is below this line is x plus y less than W. That is because you can just take it over here. Okay, when x and y both are equal to 0, okay, then W will be in this case, in this particular case, okay, what you call x plus y, if you make it equal to 0, then the 0 value will be this point. If you see over here, if you extend it here, you have some positive value of W, whereas x plus y is 0 at this point. So therefore, for this point, if you consider 0 is less than some positive value of W, which is over here. Okay, because at this point the value of W is what you call 0 plus some positive quantity of y. Similarly, at this point also it is just the same. It is, both are same. Rather, because it is x plus y is equal to W, you can take this point might be and try to see all throughout here it is x plus y is less than W, and above the line over here it is x plus y greater than W. So going on those lines, you can just say that the region corresponding to x plus y less than W is below the, what you call, a line which is nothing but x plus y equal to W. Okay, and that can be written like this: P of x comma y belonging to the region R. And once we say that, we are talking about the CDF. Now this is two variables are there, x and y, and hence we need to what you call put here a double integral in the region R with the so to say combined PDF. Now this is the PDF f of xy x comma y dx dy. F of xy x comma y dx dy. So now you have here, you can interchange the order of integration. You can write dy first and dx second, and then this what you call integrals also will get interchanged. Okay, you can assume that this is with respect to y because y is there here. This is with respect to x because you have dx here. If you write dy dx, if you change the order of integration, then this will be dy dx, and this will be with respect to y, and this is with respect to x. Okay, integration. Further to that, we already said that x plus y less than w. So if we say x plus y less than w, then what will be the quantity, what will be the value of so to say y, okay, when we provide a value of x. Okay, so that means if I take this w on this side, then this will give me y is less than w minus x. Y is less than w minus x. If I have x plus y less than w, if I take x on this side, right, x from the what you call left hand side, if shift it to the right hand side, then I'll get y is less than w minus x. So therefore, and that y less than w minus x gives us that 0 less than minus infinity less than y less than w minus x, minus infinity less than y less than w minus x. That's another way of writing it. Okay, x plus y less than w can be written as y less than w minus x, and that is nothing but minus infinity less than y less than w minus x. And that is what is written over here. The range of values of y are written over here as minus infinity and w minus x, because w is equal to x minus y, and this integration is with respect to y because we have written here dy. Okay, as well you can say that I can write dx over here, and here we will write w minus y. That's also possible. You write here dx, and this will become w minus y because we are integrating with respect to x. We need to write values with respect to x. So y will get shifted to the other position, and that hence we'll get w minus x. Presently, we are integrating here with respect to y. Therefore, this will be w minus x from minus infinity to w minus x. Okay. Now, the other thing is dx over here, where we will consider the whole of the range of x from minus infinity to x. So as x takes the values minus infinity to plus infinity, as x takes the values, this just gives us that as x takes the values from minus infinity to plus infinity, y takes the values from minus y to w minus x. If you reverse it, then as y takes the values from minus infinity to plus infinity, x will take values from minus infinity to w minus y. Okay, that's another way of representing the same thing, right? That also is possible. Okay, that also is possible. So that means in this case we can try to write here minus infinity to minus infinity. Then this will become minus infinity to w minus y because we have written here dx first. Okay, so this is minus infinity to w minus y. Okay, so let us consider first this itself. So we have just written here combining the 3.81 and 3.82. Okay, now that means in place of this I can just replace by the cumulative distribution function of w, CDF of w, and that is fww, with that is what is given in 3.81 over here, 3.81 over here. Okay, so we have written here, this is nothing but the fww, and hence we have written the same thing whatever we have written over here, right? So if you differentiate this, right, if you differentiate this, okay, 2.9 is just that you differentiate both sides. If you differentiate this, what you'll get is FWW. This is the, that is the differential of the CDF is the what we call PDF. Differential of the CDF is the PDF. We know very well that differential of the CDF is the PDF. So if you differentiate this equation with respect to W, then you will, what you call, this will be, this integral will go. This integral will go. And in place of this y, we will have the limit, which is w minus y, upper limit. The lower limit will be minus infinity. But if you substitute the minus infinity component, then we know that f of xy, x comma minus infinity is equal to 0. So we don't write that. Okay, f of xy, x minus infinity on to the negative side. If either x or y becomes minus, then the f of xy, x of minus infinity will be equal to 0. Okay, if you integrate this, naturally you will get the value of what you call so to say f of xy, capital F of xy, x minus y, because this is again the so to say the what you call PDF. So if you integrate the PDF, you'll get the CDF. So that means f of xy, x comma y. If you integrate this, and that will be f of xy, x comma capital F of xy, x comma minus infinity will be the lower limit, and upper limit will be f of xy, x comma w minus x. So first you write the upper limit, and then you write the lower limit. The lower limit is having one of the term as minus infinity, and the CDF for one of the term minus infinity will be 0. So only we are left with w, the first what you call upper limit only. And if you what you call differentiate that capital F of xy, x minus w x, x comma w minus x, x comma w minus x, then you will get the PDF. If you differentiate this is the CDF. If you differentiate the CDF, you'll get the PDF. Okay, so thus you'll get f of WW is equal to this quantity. Now, if you say x, y are independent, if you say that this is independent of this, W is independent of W minus X. Okay, so if you say that W is independent of W minus X, or X and Y are independent, you can as well write that as, this can be written as two different, PDFs for each X and Y separately. Fxx, Fy W minus X dx. Integral minus infinity to infinity. Now see this closely. Okay, see this closely. This is what integral? Can somebody tell what type of integral is this? What type of integral is this? Can somebody tell me? Have we studied in signals and system? Have we studied this integral in signals and system? Or have we studied it in maths somewhere? When we say, you have a x variable and w minus x. Now this is known as the convolution integral. And the, total, the function will be the convolution function. Okay, convolution function. So this is the convolution integral. And if I take the other way around, that is, if I take this, function wherein I'll write minus infinity to infinity and minus infinity to w minus y. Okay, in place of, the minus infinity to infinity, minus infinity to w minus x with dy dx. If I take dx dy, I said minus infinity to minus infinity and minus infinity to w minus y. Then at that time, I am going to get the other function, okay, in the same way, which is known as fyy, fx, w minus y. Okay, this is the other convolution integral. Okay, either of the two can be used. Either 3.84 or 3.83 can be used for the equation over here, and that just refers to the convolution integral. Okay, so the convolution is represented by this FWW is equal to fxx star. This asterisk over here is referring to the convolution. Okay, this denotes the convolution or refers to the convolution. So since the PDF for the random variable w is equal to x plus y is convolution, so if you add the what we call random variables x and y, then their PDFs will get convolved. What it gives us is that if we add the random variables x and y, then their convolution gets convolved. Okay, so since the PDF for the random variable w is equal to x plus y is a convolution of the PDF for x and y, a convenient relation for the characteristic function of w is available to us. So the what you call characteristic function is nothing but integrating, multiplying this with e to the power of j omega w, multiplying this with e to the power of j omega w, and integrating it will give us the convolution, because we have here for w both the variables x and y. It's a what you call function of both x and y, or rather it's a sum of both x and y. Therefore we need to take double integral. Okay, so characteristic function is double integral of this value, and this value is nothing but fxx convolution fyy, and in place of this we can write the equation which is written in 3.83 or 3.84. Either you write this or you write this. Okay, either you write that or you write this. Fine. So we have here the double integration of fxx fy w minus x dx e to the power of j omega w d omega. Okay, so this is the characteristic function, standard characteristic function which we need to consider, and this characteristic function is considered already in the module 1. Right? So if you change the order of the integration over here, you can write dw first and dx later. What you call dw first and dx later. If you take dw, only fy w minus x is a function of w, and hence fxx can be written outside this integral. Okay, fxx can be written outside this integral, because this integral is with respect to w. We don't have a w term in this, whereas you have a w term here. You can't write this outside this integral. Okay, so using the change of variables, we can write w minus x as v. If you write w minus x as v, then this w will be v plus x. W will be v plus x. So if you expand that, then that will give us e to the power of jw, okay, v plus x. So that you can separate them out. Then it will become e to the power of j omega v multiplied by e to the power of j omega x. Okay, and the e to the power of j omega x is written separately here, and e to the power of j omega v is written separately here. Okay, this I have just put it over here. W is equal to w minus x plus x is equal to v plus x. Okay, so that can be written over here. This can be written over here, and this just turns out to be v is equal to w minus x, right? Or I can write v for this, and I can write for this w v plus x, and v plus x can be separated. A to the power b plus c is equal to a to the power b into a to the power c, or x to the power a plus b. X to the power a plus b is equal to x to the power a into x to the power b. Okay, so that way you can separate the exponentials over here, and this is nothing but the this quantity you can see very clearly is the characteristic function of x, and this is the characteristic function of the y random variable. So what does that give? It just gives us that whenever we have two random variables x and y, independent random variables x and y added together to form w, then the characteristic function of w is nothing but the multiplication of the characteristic function of each of the x and y together. Okay, multiplication of the characteristic function of each of the x and y together. That is what it is giving us, right? So we have considered from w is equal to x plus y. From here we have considered mean, we have taken variance, we have taken CDF, we have considered. From the CDF, okay, we have written for CDF the equation and simplified it, and differentiated it to get the PDF, and PDF we have found it to be the convolution either this way or this way, right? And if we what you call write the characteristic function for the W, that is FWW, then we will get this equation. And if you simplify this, we will get that the characteristic function of the W, which is sum of the two independent random variables, then that will be equal to the characteristic function, multiplication of the characteristic function of each of the two X and Y random variables. Multiplication of the characteristic function of each of the random variables X and Y, which are independent of each other. Okay, which are independent of each other. Okay, so this just gives us that if W is equal to the sum of the two independent random variables, the characteristic function of W is equal to the multiplication of the what you call characteristic function of each of them, right? Multiplication of each one of them. Now let us take an example here. Now, is it clear? Is there any doubt? You can ask. If you don't have doubt, we can go forward.